Our last presenter is Eli Asarian. Eli is an aquatic ecologist and hydrologist and founder of the California-based consulting firm Riverbend Sciences. He has worked in California and Oregon watersheds for over 20 years. He specializes in statistical analysis of large, complex data sets and has authored or co-authored over 25 technical analyses on hydrology, water quality, and aquatic ecology. He has assisted with development and implementation of salmon and steelhead recovery plans throughout California. Please help me welcome Eli.
Great, thank you. Thanks, Karsha. Okay, thank you all for coming today. I'm going to talk to you about results and lessons learned from a study that I've done in two valleys of Northern California, looking at the effects of a irrigation curtailment program using remote sensing and river flow gauges. I completed a technical report back in September that's available on my website, and I'm currently working on a peer review manuscript and brought in some other folks to help me with the write-up. And I want to thank the Klamath Tribal Water Quality Consortium for funding this project. I'll start here with a little bit of background on what is consumptive use, what is ET, and how does that relate to irrigation efficiency and water budgets. So when water goes into the irrigation system, it can end up in multiple places, right? A lot of it ends up as consumptive use. We can further separate that into productive uses and unproductive uses. So productive use, that means the crop has actively used that water and it's grown and it's producing food, it's producing forage, it's doing good stuff, right? And then we have wasted water that's really not accomplishing much. So that is water that it's the wind drift and evaporative losses. So that's water that leaves the sprinkler head and then is wafted away by the wind and never reaches the crop or the ground. Water that lands on the surface of the leaves of the crop and then evaporates, or water that is evaporated from the soil. None of those really help the crop grow. So, and correct me in the Q&A session if I have this wrong, but I think that ET only incorporates those lower three things, and that wind drift is not included either in sort of ET as a concept or specifically in the ensemble ET values from Open ET. So it's important to keep that in mind. Another fraction of the water that's applied to a field is not consumed, but becomes a return flow. And in most places, those return flows are reusable. So that's either runoff that goes off the other side of the field and back into the stream, or it goes into the groundwater where it later returns to a stream, or can be pumped out later for irrigation. In some places, there are non-reusable return flows. For example, if the end of your basin is a salty lake, you can't use that for drinking water or irrigation, right? Or if your groundwater is really salty, if it goes in there, you can't use that for irrigation. So when we're trying to reduce water scarcity at a basin scale, we really need to focus on reducing the consumptive use, because that's the water that's truly lost from the system. Converting a leaky pipeline into, a leaky ditch into a pipeline, you're just sort of robbing Peter to pay Paul, and you're reducing groundwater recharge, right? You're not really saving water, because the excess water from one farm becomes either a source to a downstream farm or a source to the river. You need to focus on reducing that consumptive use. And if we're trying to do that in the least or in the best way possible, we'd want to start with reducing that wasted water, right? Because we're not getting anything for that. And then depending on how far sort of over budget we are, we might also need to cut into the productive uses, but obviously that has harms to agriculture. So how do we save water at the basin scale by reducing consumptive use? So one way is reducing those wind drift losses, right? And so Warren Peters have this great report called "The More You Expose, the More You Lose." And they talk about different sprinkler systems, and I've ranked them here on this axis from highest consumptive use to least consumptive use. And depending on how many steps you move down that chain, you could save something on the order of 5 to 20% of your water. That's real savings. It's not just avoided groundwater recharge, but it's real water saved. So you do that by moving the sprinklers as close to the ground as you can, decreasing the pressure, increase the nozzle size, and have big drops that fall straight to the ground. You still need to have uniform application across your field. And I should say also here that drip irrigation would be another step. You could save a few more percent, but that's not used on the crops in my study area. So we wanted to use remote sensing to see what was going on in our fields during these curtailments. I'm using information from 3 tools here, primarily OpenET, but also some stuff from the Climate Engine and the Sentinel Hub EO browser. These are all 3 great tools that I encourage you all to play around with. Our study area is the Shasta and Scott River valleys of Northern California. These are 2 tributaries to the Klamath River, which is one of the major salmon-producing rivers on the Pacific coast. And these fish are of great importance economically and culturally, and especially to the tribes that live in the Klamath Basin. So in 2021, the state of California declared a drought emergency. And for the first time ever, they imposed mandatory minimum in-stream flows in the Shasta and Scott rivers. In the Shasta, so these graphs here show flow data. The top one is the Shasta River. Their irrigation users, water diverters, were essentially curtailed over the course of the season by the priority of their water right. The red line there shows the observed flow in the river, and the blue line is the emergency minimum flows. And you can see that for the most part, the red and the blue track together. And the water master, who manages the versions in the system, when the river flow got too low, they would turn off progressively more and more junior rights until the river flows were met. So it worked pretty well in the Shasta. In the Scott, surface water was curtailed in the beginning of July, and then groundwater a couple weeks later. But you can see there's a period of several months in mid and late summer where the river flows are way below what the emergency minimums were. And essentially what happened was that the state allowed groundwater users to keep pumping through the use of these water conservation agreements. And I'll circle back to those in a minute. So we didn't see, in the Shasta, we saw a really strong sort of management signal on the 2022 flows. But in the Scott, we really didn't see that signal. And the flow in the Scott largely tracks that of the adjacent Salmon River, which is the bottom plot there, which is an unimpaired flow gauge. And so essentially, the flow that we saw in the Scott in 2022 was sort of what we would expect based on climate. And there doesn't appear to be a major management signal, even though there were these mandated in-stream flows. So these water conservation agreements were user-developed plans by each of the groundwater users, and in these written agreements, they promised to reduce their pumping by 30% across the irrigation season through some combination of increased efficiency, switching to less thirsty crops, fallowing corners of fields or whole fields, reducing the number of cuttings of alfalfa, like shutting off the irrigation early and only doing 2 cuttings instead of 3 or 4. There's really no meters to speak of in the Scott River. It's all estimated and self-reported usage. And almost all the groundwater users in the valley signed up for this program. So what did we see in terms of the fields? The top maps there show for mid-August the Enhanced Vegetation Index, which is just a way of measuring greenness of the fields. This is from the Sentinel-2 satellite. So the left 2 maps show the Scott River in the baseline year and in the curtailment year. And you can see that the level of greenness in the Scott is relatively similar between the 2 years. That panel in the lower left, that line plot shows the greenness across all the months of the growing season. And you can see in most months, the greenness was very close between the curtailment year and the baseline year. We see something different in the Shasta. What we see is that I've highlighted areas in blue there, where areas that were really green in 2020, but in 2022, they were much less green. So the maps are in August. If we look at the line plot in the lower right, it shows that across the whole growing season, the Shasta Valley as a whole was less green than it was in the curtailment year. Or sorry, it was, yes, less green in the curtailment year than the baseline year. So that was greenness. If we look at just some example images from the Landsat thermal band, which is a major input to the OpenET calculations, those same highlighted areas in the Shasta, you can see that evaporative cooling of the fields, right? They're nice and cool in 2020. In 2022, those fields are hot because they're water stressed because they're not being watered. So here is the OpenET ensemble values rolled up for all the fields within the Shasta River Basin. On top there is the reference ET. That's just based on the climate data. So the climate was pretty similar between the 2 years. The actual ET in orange there, we saw about a 24% reduction. Precipitation in the pink at the bottom, it went up a little bit during the growing season. And so then we calculated net ET, which is the actual ET minus the precipitation. So it's sort of a very coarse metric that sort of accounts for precipitation without getting into soil moisture and all that stuff. That net ET went down by about 32% in the Shasta. So pretty substantial reduction in ET in the Shasta. In the Scott, we saw that the actual ET went up about 1%. Once you account for precipitation, the net ET went down by about 5% because it rained a decent amount more in the Scott. So the overall ET in the Scott didn't go down, but the net ET did go down a little bit because of the more growing season rain. If we look at it on a monthly basis, we can see that in the Shasta, the actual ET was lower in every month of the growing season, whereas it was similar in every month in the Scott. Here's some maps at the field scale for each of the fields in OpenET, and the colors there are showing the percent reduction from the baseline year to the curtailment year. And you'll see that in the Shasta, that dark blue purple color, that's greater than a 50% reduction in net ET. And the bar graph just showed the same thing as the map, but just put them on it's the percent of area in the thing. So it's just easier to sort of get the quantities. So in Shasta, that biggest thing was the greater than 50% reduction. In the Scott, what we see is that the most common thing was a slight increase in net ET or a less than 10% reduction in ET. So there's two different things going on in these basins. We also looked at irrigation source. So the Scott River is primarily groundwater irrigated, and the biggest crop there is alfalfa. In the Shasta River, the biggest source is surface water, and it's mostly pasture, flood irrigated pasture. In the Shasta, we did see reductions in both total net ET volume for surface water and for groundwater. Going back to those water conservation agreements, here's just a map showing where they were across the valley. On average, there was about a 1% reduction in net ET on these ranches. Looking at net ET, there was about a 7% average reduction in net ET on the 47 ranches. There were two ranches that did have a 30% reduction in their net ET, and that was the goal of what everyone said they would do, is they would reduce their pumping by 30%. And this net ET is not like a perfect estimate of pumping, but it's probably a reasonable proxy. One of the ways I think that this happened was that it really was not a well-designed program. It was an emergency regulation. They had to get something in place pretty fast. There's no meters, there's no transparency. And so the water users had a big incentive to say that in the past they were using tons and tons of water, because they had to show a 30% reduction. And so if you could say, hey, I used to use 44 inches, and now I'm only using 29 inches, there's your 30% reduction. So I think that was a big part of what happened. Have some recommendations for the OpenET team to work on things. One is, I think, at least in our study area, and probably a lot of the West, wildfire smoke is a big deal. And it has two effects on ET. One is it dampens the evaporative demand and also messes up the satellites, right? It's just sort of like a cloud, and you get these big, long gaps where maybe for 4 weeks or a month, you have no data that needs to be interpolated. So I'd really like to see some focused research on this effects of wildfire smoke on ET and on the OpenET estimates. There's a great satellite, the Sentinel-5P has an aerosol index that's been available since June of 2018. That's a good way for assessing the level of smoke. So when you have these long gaps, it's particularly problematic when combined with alfalfa. Because alfalfa is not, there's some crops, right, that are just growing, and that are harvested and they crash, or they have a long, slow decline. Alfalfa is constantly bouncing up and down its ET during the growing season because it's being harvested and then it's got to regenerate. And so, if you have a month gap and you're connecting two peaks, that's going to give you a much different estimate for that field than if you're connecting two troughs, right? So I think finding some maybe other satellites to fill gaps and get more complete time series that explicitly represent that seasonal phenology of the alfalfa, I think would be a good thing to do. Another thing we saw is that the ET values for wheat were quite a bit higher than we were expecting. They're only the wheat was only 6 to 9 inches less per year than the alfalfa. But the wheat is not being irrigated after May or June, whereas the alfalfa is being irrigated through September. So I'd like to see some more validation on wheat. Also, we didn't really have any local validation data within our study area. So it'd be great to get more flux towers and that type of stuff out there. So in conclusion, we saw in the Shasta Valley, which is that surface water dominated watershed where the water master is regulating diversions. We did see big reductions there in ET, and we saw corresponding increases in the stream flow. In the Scott River, which was primarily groundwater irrigated alfalfa, we didn't see reductions in overall actual ET. We saw a little bit of reduction in the net ET because it rained more, so that reduced the irrigation demand a bit. But we didn't see any flow increases there, and I think that was due in good part to just the lack of transparency, the lack of metering, and that incentive that the program was basically set up to encourage people to say that they used a lot of water before and less water now. So, thank you.
Thank you, Eli. A really interesting comparison between the two geographies, and really appreciate the OpenET recommendations as well.